We can say definitely there are links between Hermes and the IXV, in the sense that when Hermes started, in fact Europe was lacking the technological know-how, and when you put an engineer to design something and he does not know where to start from, of course he finds difficulties. So finding difficulties, it means that he has uncertainties. So to have uncertainties, he has to put margins, and to put margins, it means that the design then is not optimized. And so, but in parallel, during the Hermes program, a lot of technology efforts were going ahead. For example, our thermal protection systems are inherited one-to-one from the Hermes program. The first elements of thermal protection were born within the Hermes program period and have been flight tested now this time with the IXV. So there is certainly a technological link between the two programs.
Because Hermes c'était il y a 20 ans, il y a 30 ans, non? Hermes, c'est un projet qui a 30 ans.
Hermes was, no, there are not 30 years.
No,
Hermes was discussed in the 90s. In the 90s, so it went through the early design phases, but in parallel they had started a lot of the technological developments. So the first elements, you can trace them back at the Hermes program, the first elements of this idea, and the first elements on the technology as well. But of course then we took those elements and we had brought them further with the verification of their performances on ground, their qualification, their improvements, until we brought them up to flight.
Ok. Pourquoi c'est un lifting body?
In fact, so when we started these activities, when we wanted to define the spacecraft, we started putting on the table all the possible options in terms of shapes. And classically in space design, you have three classes of vehicles. The first class is the capsule. The capsule is simple. Simple means also reliable if it works, but it has very low controllability and very low maneuverability. It means that if the deorbiting part goes wrong, then with the capsule you cannot correct it to land where you want to land. So this is the capsule. Reliable but limited in maneuverability and controllability. On the opposite side, we have the winged bodies. So bodies which have lift with wings, like the space shuttle, for example. And these spacecrafts have a very high maneuverability, very high controllability, but also very high complexity. And complexity means risks and extra cost. And we have experience in the past with the NASA space shuttle problems in flight due to this complexity. In addition, one has to consider that the real use of the wings, you do it at the very last minutes of the flight, in the last 4 or 5 minutes of the flight. And you have to bring all these mass up to orbit, uselessly, in orbit, uselessly, going through the hypersonic phase, uselessly, just to use it the last 4 or 5 minutes. So what we have decided at the time we started was to have a compromise, this lifting body without wings, so having the maneuverability and controllability similar to a winged vehicle like the shuttle, but not with the complexity associated to the wings. So it was better than the capsule and not as complex as and risky as the space shuttle. And this is where we define this lifting body shape, which is, I would say today, a masterpiece of technology, which was designed basically by Dassault Aviation in France.
Ok, by Dassault, d'accord.
Yes.
Comment?
We have landed today at a speed of approximately 6 meters per second, so 20 kilometers per hour. So you have to consider that you have to slow down from 28 kilometers per hour, 1,000 kilometers per hour, to 20 kilometers per hour. How do we do it? Basically, which is the complexity. The complexity is that the kinetic energy that the spacecraft has in orbit has to be converted into heat to dissipate the heat, so to dissipate the energy. And that's why when we cross the atmosphere with the friction with the air, basically we slow down, but to slowing down we heat up. So the vehicle has to go through the re-entry corridor, modulating the heat that it can withstand and the target landing point that it has to match, and creating temperatures around the vehicle of approximately 1,700 degrees Celsius, where every metal would melt and every system would be destroyed. So the complexity of this mission was really into surviving this very heavy environment of 1,700 degrees Celsius, maintaining the structural integrity while controlling his path to be landing at the right place where he wanted to be.
Ça signifie c'est...
The mission was designed to reproduce 100% the conditions as if returning from low Earth orbit. But when we say this, we mean that at the impact with the atmosphere, the spacecraft was supposed met the atmosphere at 7.5 kilometers per second. So in order to do this, an end-to-end mission analysis was run, and to define a suborbital mission, because we don't need to go to orbit, we are testing the re-entry. So we don't want to have the complexity to go to orbit and then to deorbit. We know how to do this, this type of activities. What we don't know today is, or at least yesterday, was how to survive the atmospheric re-entry. So we designed the mission end-to-end in order to reproduce at 120 kilometers the full return condition from low Earth orbit. And this included, in the mission analysis, the fact that we were separated by the Vega rocket at the 340 kilometers altitude, and then we were reaching 413, and then we were going down. So this is the result of the mission analysis.
Quel est l'objectif à terme du projet Pride? Donc la suite, c'est Pride.
Yes.
C'est une navette type Hermès. C'est quoi l'objectif, l'utilisation?
Yes. So the IXV mission is a fundamental element for multiple applications. So the multiple application for the long term can be one, we are here in Guyana, so one which would be very much interesting for Guyana is to have reusable launcher stages in the future. So if you want to bring back some part of the launchers to make them reusable and maybe to cut into the overall costs, then you need to go through re-entry. You have to return them on ground. So the IXV will provide fundamental elements for this. Second application, we had the successful mission of Rosetta some months ago. It was an outstanding mission. We went to a comet, and we have been landing on a comet with success. If tomorrow we want to embark on the capability to bring back samples from asteroids or from planets, and so on, this return capability is fundamental as well. So it can open also activities in this direction. Third, today we have European astronauts which come back from the ISS, or even for the future from a generic orbital infrastructure with Russian technology. Very fine, works very fine, but if one day Europe would like to start having its own system to bring back European astronauts on ground, then this is a fundamental step again. So having said this, there are multiple applications that will benefit from this know-how in Europe. For the short term, what we can say is that there is already an approved program within the European Space Agency, which is called PRIDE, Program for Reusable In-Orbit Demonstration for Europe. And the objective of this program, we have already somehow agreed with the member states on the high-level objective, which are to go to orbit, to have a system which goes to orbit, operate in orbit, and comes back on ground in order to be relaunchable. So these are the very high-level objectives. Now what we are going to do after this successful flight is we will sit with our member states and we will try to define together what type of in-orbit demonstration we want to do it. Because the idea is to have a research platform, to make a research platform that could allow Europe to go to orbit, test in orbit technologies that you cannot test on ground, for microgravity experiments, for Earth observation, for robotic exploration, and so on, and have the capability to bring them back and have a machine that can be relaunched with a different set of payloads. So basically a machine that provides a laboratory, a flying laboratory in orbit, and brings back the payloads that we put in orbit.
Est-ce qu'on peut dire que la prochaine étape, ça va ressembler au X-37 américain?
What we can say is that the high-level objectives, or let's say, the high-level elements of the mission could be considered similar of the X-37B from US. But one thing is clear 100%. We will not do military applications as X-37 does. What we will do like X-37 is to go into orbit, operate in orbit, and come back on ground. But our payloads will always be of a civilian nature.
Ok. Quand est prévu le lancement de Pride et est-ce que ça se passera à Kourou aussi?
But we had a fantastic experience here in Kourou. We don't see the reason why we should go and use other facilities worldwide. In addition, one of the basic principles of Pride is to use European launchers. So if we use European launchers, we will come back to Kourou.
Mais l'atterrissage, ce ne sera pas en Guyane.
For the landing, of course, it will depend on the mission objectives, on the mission scenarios, and of course today we didn't start this type of discussions. It is clear that the day we will start this type of discussions, we will need to really go into the details to understand and not to I mean, it has to be very well consolidated a landing scenario. We cannot just decide to land somewhere. And,
quel horizon de période, de date?
But the period, it will depend on the complexity that the mission will have after we will discuss with our member states. So if the mission is simple to achieve, then we can have a certain time frame. If it's more difficult, then we might have a longer time frame. The idea would be for us to stay within 2018, 2020 maximum.
Okay. Et comment la mission est ressentie en Italie? Est-ce que c'est très suivi? Parce que c'est quand même quelque chose qui est complètement sous leadership italien au niveau industriel. Donc est-ce que ça crée de l'enthousiasme ou alors est-ce que les gens ne sont pas trop au courant?
There is surely an enthusiasm in the space sector of Italy. Definitely there is a lot of enthusiasm, and I think we should build on this enthusiasm to the next step. Although I must say that the IXV mission is definitely a European mission. It is true that Italian industry had a leadership, but it is also true that without the French industry, Belgian industries, Swiss industries, and other partners, Spanish industries, the mission probably would have taken longer and would have not been with this success. So I would tend to say that it's a European industry, a European, let's say, mission with strong Italian industry involvement.
Ok, bon, merci pour cette interview.
Merci à vous.
J'espère qu'on se reverra pour la prochaine tir.
Ah oui, c'est sûr.
En 2000 si on est encore là.
Merci encore. Merci à vous.